Hi, it's a good day to see all of you present here. Today we are going to talk about the angular method or the Rankine'S method or the tangential method or even the deflection angle method. So they use a lot of words. Make sure you get familiar with them. But mostly people know it by the Rankine'S method. In our next questions, they don't use that word. They mostly use the angle deflection, the angle methods. So the angle deflection method, and in most cases, given this sum, they will ask you in form of a table. Given that you remember, this is the formula that they are using. This is a lecturer accredited, approved, TVET SIDAC, Gadgira Steven from Matili Technical. We can go ahead and we see something. So the Rankine'S method of tangential or the deflection angle. The deflection angle to any point on the curve is the angle between the tangent at point of the curve. So this is just the point PC, and the line joining that point to PC, that's the angle there. That is the angle, the definition, thus referring to the figure I will show you later. So the deflection angle of A is equals to the deflection angle 1 plus deflection angle 2, and that of B is the same. So this whole concept is the same as the method from the code produced. I've done a good video there. Make sure you go ahead and you look at it. So a lot I have done there, even the simple illustrations. So this, from this point, I'm just going on ahead to describe something a little bit, but the concepts are the same. So the Rankine'S method or the deflection angle is the same as the method of the code produced, but the formulas are a little bit different. So let ABC be the point on the curve, and the chords lengths are as given here. So these are the chords C1, C2, C3. The deflection angles are here. So this method is the same, and I repeat, it's the same as that of the code produced. So from the property of simple curves, I had spoken about that property on that video. Make sure you watch it. Our T1 OA is the same as the angle V. A1A is the same as 2, the deflection angle that is found there. By the formula, so the chord length C1 is equals to R multiplied by to the deflection angle, and that is gotten here. I have explained that in much more details from the code produced. How I use the one radian here is equals to pi over 180 degrees. Then I substituted all my values to the arc length, and I got to the deflection angle multiplied by r. So that is done there. So if our deflection angle is in radians, this how this formula is done, and I've done it here well, and I have illustrated it in a much more details in the other video. Make sure you look for it, the video under the code produced. Yeah, so by having that my formula, so here I multiply directly, just like how I've done here. The 1 radian here, I again change it back. So this will be r multiplied by 2, the deflection angle multiplied by, so if the deflection angle is in radians, so 1 radian is equals to pi over 180 degrees, a concept found in high school. Yeah, and even in the lower schools, the primary, I think, yeah, even in the grade levels, the concept is found. So this formula becomes 2 multiplied by so this r multiplied by 2, the deflection angle, which is in radians. That means we have to multiply the pi over 180. So, and that we have converted it back to the degrees. Remember that. So by changing this simple mathematics, so r multiplied by this, I want the deflection angle to remain on one side. I will divide here, so here will be multiplied by this is 180 over pi. Then here the r will divide here by r, will divide here by 2. The same will be done here, and if we divide that, my answer, so c1 was equal to everything here. So here we had c1, so c1 multiplied by 2r, so here we had c1 is equal to that. So c1, here we divided 2r, the same was done here, r and the 2, so it cancelled everything and we remained with our deflection angle there. So our deflection angle is equals to c1, this is the chord length here, chord length, over 2r multiplied by 180 over theta in degrees, remember that. And if that is in degrees, you remember that will be multiplied by 60 minutes. By the use of a calculator, you can multiply all the values found here. By multiplying all those values, we'll have 1718.87 c1 over r minutes. The same will be done to the other deflection angles. They will, nothing much will change, only the chord length. This is the formula. People were asking me where I got this formula from. So this is how this formula is gotten in the deflection angle method, or the Rankine'S formula. So the deflection angles are gotten directly. Make sure you use your calculator well here, and use the pi found in the calculator, not the one that you think in your mind that is 3 point something. Yeah, not that. Use the calculator one, because that is the right one with all the full decimals found there. So these are the two, so this becomes my deflection angle 1, deflection angle 2, and any other will have the same. So that figure, this the same representation of the figure and the chord produced. So by adding the total deflection angles that you will have calculated there, will have this. So the summation of all those deflection angle divided by 2 will be equal to that deflection angle that is found there. So when you want to know if you have done the right thing, you add all the deflection angles, then you divide them by 2, and by dividing them by 2 you'll have gotten to proven if your sum is right. So every deflection angle should be equal to pi over that is theta over 2. All the deflection angles should be equal to that. This figure is similar to that. You can pause, you can draw it. If you are writing some notes, this will be helpful. Let's go directly to an example. So two tangents intersect at a chain edge of 1250 meters. The angle of intersection is 150 degrees. Calculate all the necessary data for setting out a curve of radius to 50 meters by the deflection angle method. That's how Nick also put it. So the peg interval is 20 meter. Prepare a setting out table when the least count of the vernier is this 20 seconds. Calculate the data for the field checking. So the field checking is the addition of all those deflection angles. When divided by 2, it will give you the original deflection angle that you had calculated. Here we are, so the radius here, the deflection angle. So this is the angle of intersection. By minusing it by 180, you'll get the 30 degrees. Chain edge of intersection, it is given. Peg interval, this is this C1, or the chord length is 20 meter. Then the vernier, it is calibrated, so there the count of 20 minutes. Number 1, so the tangent length, the formula of calculating that the tangent length, this is r tan theta over 2. By the use of a calculator, make sure you use the calculator properly. So this is tan 15. If you have a simple calculator, make sure you divide first before you turn that. So if you turn 30 divided by 2 using a normal calculator, it will give you the wrong value. Remember that. So here we calculate again the curve length, the formula of calculating the curve length, that is theta r multiplied by the angle, so that is multiplied by pi over 180 degrees. So our r found on the on the question, this is 250, multiplied by 30 degrees over 180, you get 130.85 meters. Change of the first tangent point, so t1 is equals to the change of intersection minus the tangent length, and you get our answer there. And then t2 is equals to t1 plus the curve length, and by adding the curve length we'll have gotten our answers 13.89 meters. By doing that, we go ahead to the next part of calculating our answer. So the first subcode is 17 meters, and that 17 meters is done just like this. You go ahead, so this t1 is 118, that's 1183. You divide it by the number of peg interval, that is 20 meter. By dividing that with the number of peg interval, make sure you use your calculator properly in order for you to get accurate results. You input that value in your calculator there, and you make sure you have inputted that well. So that is 100 and that is 1180 divided by 20. So 20, that is the distance. So here we get we have 59 full chains, and we after getting the 59 full chains, you go back. So I want to find the distance that remained there, so you multiply the 59 full chains with the peg interval that we have calculated there. And again, make sure you use your calculator well. By multiplying that, we'll have 1180. That means the value that is remaining here, it is 3 meter. So that is the 3 meter, the value that is remaining when you have your curve. By drawing a curve. So from here t1, we had a remaining distance of 3 meters in order for us to reach t1. This is what has shown us, but here we had full chain edges of 20 meters, and in our full chain edges of 20 meters, that means when you entered the curve, because we are using the curve, our distance, our full chord was 20 meters. So 20 minus 3, we get the remaining distance that was covered from t1 to the point where we have, and that distance gives us the first subchord as 17 meters. Then all our other subchords will be 20 meters. Then we go back here. We had here the curve length. The curve length is 130. You use your calculator properly. That is 130.89. That is the curve length that we calculated there, and we have already eaten 17 there. So by the use of your calculator, so that is 130.89 minus 17. When you minus 130 minus 17, you remain with 100 and you remain with 113.89. So this is the distance that remained when covering your curve. So there we had 17. This is the first subchord. Then we have the remaining distance. So I need to know how many full chords are there here. You divide that by 20 meter. So this is 113.89 divided by 20, and as you can see we have 5 full subchords. So by dividing this you'll get 5 full subchords. So our 20 meter interval here, we have 5 full subchords, and we want to know the distance that remained. So that is 20 multiplied by 5. By multiplying that we'll have 100 minus what we had here, our last distance, the last subchord, becomes 13.89, and that's how I got my C1 and the last C. Then here we had all our full subchords. Yeah, that's how we get the subchords. After finishing that, you go back to our formula. Our deflection angle 1 is equals to 1718.9 multiplied by C1 over this is 250, the R. Using your calculator, after doing all this, remember to divide it by 60, because our formula was in minutes that we had calculated earlier. Our formula was in minutes here. So you remember to divide it by 60 in order to make sure you have all your values up to the last, and the last is the second part. So 1 minute is equals to 60 seconds. You do the rest. Make sure you remember you divide it by 60 in order for you to get our deflection angles. Then the total deflection angle, I apply the arithmetic check. So by adding, so this added by this 2 degrees 17 minutes, that 1 second multiplied by 5, then we add the last one, you'll get your final answer as 15 degrees. By doing that, here is our last part. So I have input that value in a table form. So this is a table form. We have the point, change, the chord length, deflection angle, the total deflection, the angles to be set, and the remarks. So here we had from T1, this point 1, 2, 3, 4, 5, 6, and the last T2. We first start with the T1 here under the changes. Here we had no data because that is a point. Then on the second point we had the chord length of 17. So we add 17 by our change of T1, you get 1200. You do the same, the chord length found here, you add to point 1, you get 0.2. The chord length found on point 3, you add that to the change at point 2, you get the change at point 3. The chord length, so here we had 5 full chords of 20. So by adding that to the previous points, you get the chords there. Then on our last part, the last subchord is added to the P6, and that proves that our T2 is right. So this is the T2 that was found when we were calculating our answer there. So you remember to check that. So that is the same answer as that. And then we go, so these are the values that we had gotten in our calculation. So these are the deflection angles. Here we had 5 similar deflection angles. Then we had the last deflection angle that we had calculated here, remember. So these are the values that we are speaking about. And then on our last so the total deflection angle, you add going downwards. So the first deflection angle added by the second, you get that. This added by this, you get that. You add this to this, you get that. Add this to this, you get that. This to this, you get that. And this to the last, you get the final answer. Then angles to be set, you can round it off to the nearest whole number. I've used the seconds part, so I've rounded off all the total deflection angles to what you can see there, and when you round it off you get your final check. And then on the remarks, so this is the start of the curve, this is the end of the curve. And in our remarks, you remember on the remarks part, you will input this. So when the least count of vernier is, so everything here, the least count of vernier is in 20 seconds. So remember to add that on the remarks. This is just a simple illustration. You remember to watch more other related videos, and you'll get the more better concept of everything. That will be all for